Okay, let's unpack this. For us software developers, generating, truly random numbers on a classical computer, it's always felt a bit like smoke and mirrors, right?
Definitely. We use them everywhere. Crypto keys, session IDs, testing.
Exactly. But we kind of know they're just outputs from algorithms based on like the system time or maybe some hardware noise.
Yeah, or even physical phenomena. I remember hearing about Cloudflare's lava lamp wall for entropy. Fun idea, but
But it's still feeding into a deterministic process, fundamentally. It's not really random in the mathematical sense.
that's the crux of it, technically speaking. Classical computers are deterministic machines. Same input, same algorithm, always the same output.
So it's pseudorandomness. Looks random, passes tests, but if you knew the starting point, the seed, and the recipe.
You could predict the whole sequence. And for the high security stuff we build, that theoretical predictability, however hard to exploit, well, it's always there, a potential weakness.
Which is why this new research is so interesting, just published in Nature. They're talking about certified randomness from a quantum computer.
hmm
Think about that. Random numbers with a guarantee of unpredictability. For us building secure systems, could this change how we handle things like keys? Move away from just relying on difficult math problems?
It points towards that possibility, yeah. The core idea is tapping into something fundamentally different: quantum mechanics.
Right, not mimicking randomness, but harnessing it directly.
Exactly. Because at the quantum level, things aren't always definite until you look. Think qubits. They can be 0 and 1 at the same time in superposition.
Like the classic spinning coin idea.
Sort of, yeah. And when you measure it, force it to choose 0 or 1, the outcome is inherently probabilistic. Random in a way classical physics just isn't.
That unpredictability.
Yeah.
That's the entropy they're talking about.
Precisely. That's the source they're tapping into, not an algorithm, but the nature of reality at that scale.
Okay, so let's maybe reiterate why our standard ways fall short. Just to be
Big
clear for everyone listening, especially developers focused on, solid security.
Sure. The big limitation, as we said, is determinism. Classical PRNG's pseudorandom number generators start with a seed, a number.
And an algorithm, often a well-known one.
Right. And that seed plus that algorithm dictates everything that follows. If an attacker can figure out or guess that seed,
The whole game is up.
yeah,
The random sequence is completely exposed.
yep. Even adding things like system time or mouse movements helps. Makes the seed harder to guess, but it doesn't change the fundamental fact. It's still a deterministic function calculating the next number based on the current state. There's no real choice happening.
It's just complex calculation, not true chance. Which brings us back to quantum mechanics. That's the genuine source.
It appears to be, yes. Properties like electron spin, photon polarization. When you measure them, the outcome isn't predetermined in the way a classical calculation is.
There's no hidden instruction saying B spin up this time.
Not according to standard quantum mechanics, no. It's fundamentally probabilistic. Even with perfect knowledge of the system before measurement, you can only predict the probabilities of different outcomes, not the specific result. That's the entropy, real unpredictability.
Okay, so quantum mechanics gives us randomness. But the research term was certified randomness. What does that certified part actually mean for us? Why is that label important?
That's crucial. Certified means they don't just claim it's random based on the quantum source. They have a protocol, a method to verify and quantify the amount of randomness the entropy produced.
So it's like getting a certificate of authenticity for the randomness.
In a sense, yes. It provides mathematical proof that the output contains a certain minimum amount of unpredictability. This is totally different from classical generators. They might look random, pass statistical tests.
But there's always that theoretical possibility of prediction if you knew the seed and algorithm.
Exactly. Certification aims to rule that out based on the protocol and the physics. The idea, as some earlier papers pointed out, is unpredictability to any observer, even one with immense power. That's the gold standard for privacy and security.
Unpredictable even in principle. That sounds like something you'd want for, say, generating long-term cryptographic keys. How do they actually do it? What was the setup?
They used a Quantinuum H21 quantum computer. It's a trapped ion system with 56 qubits, and they accessed it over the internet.
So a remote quantum server.
Right. And the core protocol involves something called random circuit sampling, RCS. Here's the flow, thinking like a developer. Your local machine, the client, generates some challenge quantum circuits.
Okay, What's special about these circuits?
They're designed not to compute a specific answer easily, but to produce output distributions that are very complex and hard for a classical computer to simulate quickly. And here's a neat part. The client uses a small classical pseudorandom seed, just 32 bits in their case, to generate these complex quantum challenges.
So you don't need a huge secret random key to start. You use a small standard seed to bootstrap the quantum challenge generation.
Exactly. Then these circuits are sent to the quantum server, the H21. The server runs them and sends back the results, which are basically strings of zeros and ones from measuring the qubits.
But how does the client know the server actually used the quantum computer and didn't just fake it somehow, maybe with a fast classical simulation?
That's the verification step. The client takes a subset of the results and calculates a score called the cross-entropy benchmarking score, or XEB.
XEB.
Think of XEB as a measure of how closely the server's results match the expected complex probability distribution that only a quantum computer should be able to produce efficiently for these specific circuits. A high XEB score is strong evidence that quantum computation actually happened.
So the client issues a challenge that's believed to be classically hard, gets results back, and the XEB score acts like a fingerprint saying, yep, this looks quantum.
That's the essence of it. Plus, there's a strict time limit.
To prevent slow classical simulation.
Precisely. The client sends circuits in batches and sets a deadline. If the server takes too long to return the results for a batch.
The client just throws them away, assumes something fishy might be going on or wasn't quantum.
Exactly. Failed batches are discarded. This forces the server to rely on the speed advantage of the quantum hardware. They use batches of 15 or 20 jobs, ran checks before sending, and had a specific time formula based on the batch size.
Makes sense. Control the time, check the quality with XEB. What determined if a batch was ultimately good enough to contribute to the certified randomness?
They calculate the average time taken per sample, let's call it 2-key jaw, and the XEB score on a test subset, XEB test. Before the experiment even starts, they define thresholds. A maximum allowed time, 2 threshold, and a minimum required XEB score.
Okay, preset benchmarks.
Right. To accept the data and certify the randomness from it, both conditions must be met. The measured time TTP must be less than or equal to threshold A, and the measured XEB test must be greater than or equal to threshold.
So fast enough and quantum enough.
That's the idea. These thresholds are carefully chosen based on what the specific quantum hardware should achieve if working correctly, and what's considered infeasible for classical simulation within that time limit.
It's a performance contract, almost, guaranteeing the quantum nature of the process.
You could think of it that way. And they also considered security against a sneaky server.
Like one that tries to cheat. Maybe uses the quantum computer sometimes, but tries to slip in classically simulated results other times?
Exactly that scenario. An adversary trying to pass the XEB test while minimizing actual quantum computation, maybe to save costs or for other reasons. Their security analysis assumes the adversary has bounded classical power they benchmarked against the frontier supercomputer as a hypothetical limit.
So they factored in a powerful classical adversary.
Yes, and the protocol's security relies on ensuring there's a big enough gap between the fidelity an honest quantum server can achieve quickly and what a cheating, mostly classical server could possibly mimic within the time limit threshold. There's a mathematical condition involving these factors that needs to hold.
Okay, so they run it, get the results, verify the time, and XEB score. Are the raw bit strings coming out of the quantum computer ready to use as random numbers in my code?
Not quite. The raw output isn't perfectly uniform. Its distribution depends on the specific random circuits used. So there's a final post-processing step, randomness extraction.
Like smoothing it out.
Essentially, yes. They use a mathematical function called a randomness extractor in this case, a specific type called a topbits extractor to convert the somewhat biased raw quantum output into a shorter string of bits that is statistically very close to perfectly uniform. And importantly, the extractor itself doesn't compromise the randomness.
Okay, so extractors turn high entropy but non-uniform bits into nearly perfect uniform random bits. What was the final yield? How much certified randomness did they get?
From about 30,000 valid 56-bit samples, they successfully extracted and certified 71,313 bits of entropy.
71,000 bits. And that was generated starting FEM.
Just a 32-bit classical seed to define the initial challenges.
Wow. So that's genuine randomness expansion. You put in 32 bits of pseudorandomness and get out over 70,000 bits of certified true randomness.
That's the key result, yes. They reported their measured average time per sample was about 2.15 seconds, and the XEB score was 0.32. Both met their thresholds, 2.2 seconds and BT of zero point 0.3. They also put a number on the classical simulation cost something enormous, like 90 exava FLOPS on Frontier, reinforcing the quantum advantage needed.
That comparison really drives home the certified aspect. Okay, bringing this back to us developers, what are the big takeaways here? What should we be thinking about?
Well, the biggest one is the potential impact on cryptography. So much of our current security relies on problems like factoring large numbers, which we think are hard for classical computers.
But might be easy for future quantum computers, the whole Q-day concern.
Exactly. But if your cryptographic keys are generated using randomness certified by quantum mechanics itself, their security doesn't depend on computational assumptions anymore. It depends on the laws of physics being unpredictable in this way. That's a potential paradigm shift towards fundamentally more robust security.
That's huge. Instead of an arms race between code breakers and crypto designers, you ground security in physical law.
Mm.
What else? Any other areas this could impact for software folks?
Anywhere verifiable unpredictability is needed. Think about ensuring fairness in things like online gaming, lotteries, or maybe selecting participants for clinical trials run via software. Even generating truly unbiased data sets for scientific simulations or certain AI training tasks. Anywhere trust in the randomness is absolutely critical.
Right. Anywhere you need to prove the dice weren't loaded, essentially. Now, obviously, this is still research. What needs to happen next for this to become, practical?
The researchers are clear it's a step. Key improvements needed are in the quantum hardware itself. Better fidelity, meaning fewer errors in the quantum calculations and faster execution speeds.
Faster speeds and fewer errors would mean.
Higher bit rates generating more random bits per second and potentially stronger security proofs, allowing for even tighter verification thresholds. They mentioned aiming for rates comparable to existing public randomness beacons, like NISTs, as a future goal.
And what about classical computers getting better at simulation? Does that break this?
It's a factor, yes. As classical simulation methods improve, the hardness assumption needs to be reevaluated. But the researchers note this is sort of a symmetric challenge. Improvements in classical computing can also potentially help the client verify results or design even harder challenge circuits. It's an ongoing interplay.
So it seems we're not quite at the stage of importing a quantum random library into our projects tomorrow.
Hey, probably not tomorrow, no.
But this work clearly shows it's possible. It provides a concrete demonstration and a path forward. We're seeing certified randomness generated by a quantum processor overcoming those classical limits.
That's the key message. It's an experimental proof of concept showing that we can leverage quantum mechanics to generate randomness with a level of assurance classical methods just can't offer.
It definitely makes you pause and think. For us developers, consider this. What if you really could access a source of randomness you could mathematically prove was unpredictable? How would that change the way you design secure protocols, handle keys, or ensure fairness in your applications? What new kinds of secure or unbiased systems could you build if that fundamental building block was truly solid?
It opens up some fascinating possibilities down the road.
Absolutely. If you want to get into the nitty-gritty details, the Nature paper is definitely worth exploring. For now, though, that wraps up this deep dive.